Alright, so we want to extend GCD-ness from PID to a superring containing the PID. So let's see here. First, we will use the fact that D is a GCD of A and B if and only if the ideal generated by A and B equals D. Okay, so this is in a PID. D is a GCD of A and B if and only if the ideal generated by A and B is the ideal generated by D. And I tried to look through the text. I didn't see this proved anywhere. It's a fairly easy fact and it's fairly useful. So I was a little surprised by that, but I mean, whatever. It very well may be in there, and I just missed it when I was like skimming through. But anyways, we're going to prove it since it's not bad and it's important for understanding principal ideal domains. So note that if D divides A, so D is a GCD of A and B, so it's a divisor of A and B. So D divides A, which implies that the ideal generated by A is contained in the ideal generated by D. And likewise, D divides B implies that B subset of D. And so putting these together, the union of these two ideals is precisely the ideal generated by A and B. Ooh, is that right? It should be. Even if it's not right, it shouldn't be far from the truth. So if you take something in A, B, then it's going to be of the form D1A plus D2B for D1 and D2 and D. And okay, so I guess this is here. So let's write this out. So C is an element of AB if and only if C can be written as a linear combination of A and B with coefficients in our PID capital D. And we're able to combine things like this because of commutativity. And this is obviously, so C is equal to this plus this, which is contained in D1A is obviously contained in the ideal generated by A, plus the ideal generated by B, which is equal to, and this is contained in the ideal generated by D plus. So rather, this should be an implies. If C is in A, B, then C is equal to this, which is contained in this, which is a subset of this, which is precisely equal to D. And thus, AB is contained in B. Okay, so that's one direction. Now, since D is a PID, this ideal is equal to the ideal generated by C for some C in capital D. Then C divides A, and C divides B. So since D is a GCD of A and B, we know that C divides D. And so the ideal generated by D is a subset of the ideal generated by C. Remember, so if you have C divides D, then ideal generated by D is contained in ideal generated by C. That should be like automatic for you, and it's pretty easy to convince yourself of that. You just think, oh, well, C divides D. That means that D is some multiple of C, which means that the element D is contained in the ideal generated. Yeah, which means that the element D is contained in the ideal generated by C, which means that the ideal generated by D is contained in the ideal generated by C. So there you go. So D is contained in C, which we know is equal to AB. Hence, AB equals D. Okay, so that's done with that. And that you should just keep in mind. Hopefully, I won't. If this ends up being useful in other exercises, then I probably won't prove it again. But I don't know. We'll cross that bridge when we come to it. So let us, because we're going to be dealing with two rings here, we're going to denote by D sub D the ideal of capital D generated by the element D in capital D. Okay, so since D is a PID, we know from what we just proved previously that the ideal generated by A and B and D is equal to the ideal generated by D and D. Sure how much I'm going to have to scroll down. Should be fine. Since that is not a forwards E, since E contains D, we have, so the ideal generated by A and B and E is equal to the ideal generated by A and B and D in E. And that's, you can just convince yourself of that. Because if you take something here, if you have like AE1 plus BE2, then you just consider this as yeah, I'm blanking on some of the deals right now, but this is a pretty straightforward thing. The fact that D is contained in E should make this obvious. But anyways, we know the thing on the inside is this. And so, but the ideal generated by, so this is, but since D is a subset of E, again, we can just pull this out. So D divides A, and D divides B in E, and if C divides A and C divides B in E, then C equals AE for some E in capital E. So C is in the ideal generated by A and B and E because, in particular, C is contained in the ideal. C is contained in C is an element of this, which is a subset of this. But this we know is equal to this. So D divides C, and hence D is a GCD of A and B and E. And that's exactly what we wanted to prove, and so this completes our proof.